Right now, sealed beneath more than 40 kilometers of ice on a world where surface temperatures plunge to around 220 degrees, 364 degrees colder than liquid nitrogen, cold enough to freeze methane and carbon monoxide. Solid, there's a liquid ocean. It's been there for billions of years, sitting in total darkness under the ice, untouched and unchanging. It's saltier than most of Earth's oceans by an amount scientists have calculated and independently confirmed. And it's almost certainly liquid at this very moment. We only know about it because of a spacecraft that flew past Pluto 11 years ago, data that researchers are still combing through in 2026. Subscribe before we go further, because what NASA has pieced together over more than a decade about what's hidden beneath Pluto's ice is one of the most surprising best evidence findings in planetary science. Let's start with why it's so unexpected, because by all rights, Pluto shouldn't have a liquid ocean at all. Picture Pluto, and you picture something frozen, dark, and lifeless. It orbits roughly 39 astronomical units from the Sun, almost 40 times farther out than Earth. Sunlight arrives so weak that even at Pluto's noon, the sky looks essentially like night, with the Sun reduced to a bright point rather than a blazing disk. It's so cold there that nitrogen, methane, and carbon monoxide substances that are gases or liquids on Earth freeze into solid layered ice sheets across the surface. Pluto is about a sixth of Earth's diameter, and just 0.2 of its mass. Every intuitive expectation says it should be a dead, frozen ball of rock and ice, about the last place you'd look for liquid water. And yet the evidence says otherwise. Several independent lines of evidence built from data the New Horizons spacecraft gathered during its July 14, 2015 flyby and analyzed in the years since consistently point to a liquid water ocean beneath Pluto's icy crust, likely more than 100 kilometers deep by some estimates, and almost certainly still liquid today. This isn't a shaky marginal case. The evidence stacks from multiple independent physical mechanisms, each pointing to the same conclusion. Before diving into the evidence, it's worth appreciating New Horizons itself, one of the most remarkable spacecraft ever flown. It launched January 19, 2006 from Cape Canaveral as the fastest spacecraft ever launched at the time, leaving Earth at roughly 5,500 kilometers, fast enough to pass the Moon's orbit in just 9 hours. A Jupiter flyby in February 2007 used the planet's gravity to add another 14,000 kilometers. By the time it reached Pluto in July 2015, it was moving at about 49,600 kilometers, nearly 14 kilometers every second. At that speed, there was no fuel budget to slow down and enter orbit the way Cassini did. At Saturn, New Horizons had one shot a rapid flyby with its closest approach, lasting only minutes, cameras and instruments running flat out to capture as much as possible before Pluto vanished. Behind it, closest approach came on July 14, 2015, passing within 2,500 kilometers of the surface, close enough to resolve features just a few kilometers across. What it found stunned the science team. Instead of a dead, cratered ball of ice, New Horizons revealed mountain ranges of water ice rising over 3,500 meters, plains of slowly churning nitrogen, ice cliffs of frozen methane and carbon monoxide and geological variety rivaling the inner solar system. Its long-range camera LORRI captured what became some of the most iconic images in spaceflight history, especially the first full view of Pluto's heart-shaped region, which made headlines worldwide. Transmitting all that data back to Earth took 16 months, limited to about 1 kilobit per second, given the distance involved, but every bit has proven scientifically invaluable. 11 years on, researchers are still mining that dataset for new discoveries. After Pluto, New Horizons pushed deeper into the Kuiper Belt, flying past the object Arrokoth 2014 MU69 on January 1, 2019, the most distant planetary encounter ever attempted, some 6 billion kilometers from the Sun. The spacecraft is now roughly 60 AU out, with its mission extended through the late 2020s to keep studying the Kuiper Belt environment. But its most enduring legacy is almost certainly what it revealed about what's hiding beneath Pluto's frozen surface. To understand the evidence, you need to know about Sputnik Planitia, the left lobe of Pluto's famous heart, officially part of the region called Tombaugh Regio, named for Pluto's discoverer. It's a massive basin, roughly 1,000 kilometers across, filled with nitrogen ice, dotted with waterous hills, carried along by slow nitrogen flows and marked by polygon-shaped convection cells, where warmer ice rises and cooler ice sinks, a slow churn driven by heat from Pluto's interior. It formed when a large impactor gouged out a deep crater billions of years ago. The first hint of a hidden ocean came from simple geometry. Sputnik Planitia sits almost exactly on the line connecting Pluto to its largest moon, Charon. That's not coincidence. Pluto and Charon are tidally locked, and tidal locking tends to orient a body's unusually massive regions. either directly toward or away from its companion. For Sputnik Planitia to land in that exact spot, it needed to represent extra mass, not less. But it's filled with light nitrogen ice. So where's the extra mass coming from? Researchers modeled the original impact and what would happen to Pluto's interior afterward. And the models showed that denser material from below would well upward to fill the gap left by the excavated crust, and that material had to be liquid water, since water is denser than ice and would naturally rise to fill the basin. Brandon Johnson of Brown University, who worked on these models, said plainly that the scenario requires a liquid ocean, and that the ocean needed to be at least 100 kilometers thick to produce the mass anomaly actually observed. The second major clue comes from Pluto's surface tectonics. When a subsurface ocean freezes, it contracts, squeezing and wrinkling the crust above into compression features. When it stays liquid, or even expands slightly as water shifts between ice phases, the crust stretches and cracks instead, producing rifts and troughs. New Horizons found Pluto's surface covered in exactly these stretching features, with no sign of the global compression a fully frozen ocean would leave behind. A 2016 study led by Noah Hammond at Brown University pointed out that the absence of compressional features meant ice 2s, a dense ice phase that forms when high-pressure liquid water freezes, hadn't formed, meaning the ocean underneath had never fully frozen. Their thermal models suggest the ocean has likely stayed liquid continuously since Pluto formed 5 billion years ago, kept from freezing by heat from the slow radioactive decay in Pluto's rocky core. The ice shell itself, estimated at 40 to 80 kilometers thick in a 2024 analysis by Alex Nguyen and Patrick McGovern published in Icarus, acts as an insulating blanket. But ice alone may not fully explain it. In 2019, researchers from a group of Japanese universities and the University of California proposed an added layer between the ocean and the ice shell. Gas hydrates crystal structures, where methane molecules sit trapped inside cages of water molecules. This layer would insulate far more effectively than plain ice, and it would explain a puzzle at Sputnik Planitia models. Predicted the ice shell's underside should be flattened by heat and pressure from below, but it isn't. Its actual shape matches a gas hydrate layer far better than it matches a plain ice-water boundary. The 2024 Nguyen and McGovern study went a step further, using stress models based on the fracture patterns visible in New Horizons imagery to actually estimate the oceans. Properties Nguyen described finding a Goldilocks combination of density and shell thickness that reproduces the exact fracture pattern seen on Pluto. A lighter ocean would leave more fractures, a denser one, fewer. The pattern that's actually there pins the ocean's density to about 8 saltier than Earth's average seawater, with a depth somewhere between 40 and 80 kilometers, likely wrapping the entire planet beneath the crust. It's salty enough that a person placed in it would float as easily as in the Dead Sea. There's also independent geological evidence. An October 2023 study led by Dale Cruikshank at the University of Central Florida, published in Icarus, examined a feature called the Kaladzi crater, northeast of Sputnik Planitia. It's an unusual crater missing the central peak that normally forms from impact rebound, slightly stretched out of shape in a way consistent with tectonic stress, and surrounded by an unusually strong concentration of water ice, standing out against the methane ice that dominates most of Pluto's surface. Cruikshank called this combination the giveaway that something different happened there. He attributed the water ice to cryovolcanism, a cold analog to volcanic eruption, where waterous slurry is forced up through the crust by internal pressure rather than molten rock. Kaladzi appears to be the site of just such an eruption, with ocean material pushed to the surface. That puts Pluto alongside Europa, Enceladus, and Titan as another world, showing direct surface evidence of an active internal ocean. Zooming out. Pluto's ocean isn't just a curiosity, it reshapes how planetary scientists think about the outer solar system generally. A decade ago, the solar system's known or strongly suspected ocean worlds were Europa, Enceladus, Ganymede, and Titan, all moons of giant planets, where the host planet's gravity flexes and squeezes the moon as it orbits, generating tidal heating that keeps subsurface water liquid. That mechanism is well understood and doesn't apply to Pluto at all. It has no giant planetary neighbor providing tidal heating. Its only heat sources are leftover formation heat and the slow radioactive decay of uranium, thorium, and potassium in its rocky core, much weaker sources than tidal flexing, which is exactly why scientists originally expected Pluto to be frozen solid throughout. The finding that these comparatively weak heat sources, combined with a thick insulating ice shell and possibly a gas hydrate layer, have kept an ocean liquid for the entire age of the solar system changes the calculus entirely. If Pluto managed it without tidal heating, than any sufficiently large icy body that retained enough formation era. Radioactive heat could potentially do the same. The Kuiper Belt, the vast ring of icy bodies beyond Neptune, where Pluto orbits, contains hundreds of thousands of objects over 100 kilometers across, and potentially several hundred large enough to qualify as dwarf planets: Eris, Makemake, Haumea, Sedna, Quaoar, Gonggong, and more, all sharing the basic traits that let Pluto hold onto its ocean. If the models built around Pluto generalize, many of these bodies could be hiding liquid water of their own right now. This has real implications for where life might exist, not in some other star system, but right here. Life on Earth is thought to have originated near the deep ocean floor, where water chemical energy from hydrothermal vents and biology's raw ingredients could interact for millions of years, shielded from surface radiation. In extremes, Pluto's ocean offers exactly that kind of sheltered, stable environment, protected by 40 kilometers of overlying ice from the outer solar systems. Harsh radiation kept liquid by heat rising from the rocky core below, and potentially in contact with that core in ways that could drive the same hydrothermal chemistry many scientists think kickstarted life on Earth. NASA has drawn this connection explicitly, noting that life in Pluto's relatively warm subsurface ocean would be shielded from radiation and impacts, much as early Earth life is thought to have been in the deep ocean. Whether anything actually lives there is completely unknown. But the basic ingredients, liquid water, chemical energy, radiation, shielding, long-term stability, are all present. New Horizons was a flyby mission. No ability to land drills or sample anything. It gives strong evidence and lets scientists estimate the ocean's properties, but it can't deliver absolute confirmation the way a dedicated orbiter or lander could. There have been proposals within the planetary science community for a dedicated Pluto orbiter and lander that could map the ice shell with radar study, the ocean's chemistry through molecules seeping through the ice, and check for ongoing cryovolcanic activity. Such a mission would take roughly 15-20 years to reach Pluto with current propulsion. Nothing has been formally approved or funded yet, but the scientific case keeps getting stronger with every new paper. What all this really tells us is that a large liquid ocean doesn't require a nearby giant planet for tidal heating. All it takes is a body large enough to retain enough radioactive heat from formation wrapped in an ice shell, thick enough to trap that heat, possibly helped along by an insulating gas hydrate layer. How many bodies out there meet that bar? Nobody knows yet, but it looks like a lot more than anyone expected. A 2020 study in Nature Geoscience, led by researchers including Carver Beerson at Arizona State University, concluded that Pluto has most likely kept its ocean continuously since formation, and suggested subsurface oceans may be far more common in the outer solar system than previously thought in a region once assumed to be simply too far from the sun for liquid water to survive at all. And Pluto's own surface tells this story in a way that's hard to unsee once you understand it. That famous heart-shaped feature, Tama Regio, the image that became the face of the New Horizons mission, and one of the most recognizable planetary photos of the last decade, sits directly over the spot where scientists believe Pluto's ocean is closest to the surface, where the ice shell is thinnest, where cryovolcanic material has most recently pushed up from below, and where Charon's tidal pull is orienting Pluto in a way only a dense internal ocean can explain. The most photographed, most emotionally resonant feature on the most distant world ever visited by a spacecraft is, in a very literal and measurable sense, the visible signature of a hidden ocean, one that's been sitting in the dark and cold more than 5 billion kilometers away, since before life existed on Earth, waiting for a spacecraft from a small blue planet to finally fly past, fast enough to capture it. If you want to keep following this story as NASA's Pluto research continues, as the case for a dedicated orbiter or lander mission builds, and as future analyses refine what we know about the oceans, depth, salinity, and chemistry, subscribe now, because there's almost certainly more to learn about what's hiding under that heart-shaped ice and what it means for how common liquid water really is in the solar system's cold outer reaches. Every new paper from the New Horizons dataset adds another layer to a story that's already among the most surprising in planetary science, a world once written off as a frozen dead leftover from the early solar system that turned out to be hiding an ocean older than Earth's own. Let me know in the comments what struck you most, that Pluto has kept a liquid ocean hidden for 4 or 5 billion years, the Goldilocks calculation that pinned its salinity to dead sea levels, using nothing but ice fractures, the cryovolcanic eruption at Kaladzi crater, the fact that the famous heart sits right over the thinnest ice above the ocean, or simply that the most distant world ever visited turned out to be an ocean world all along. Thanks for watching all the way through. See you in the next one.